Okay,
Hello
go ahead.
everyone.
Thank you.
Thank you. Hello everyone. I am Upasna Baweja and I will discuss about my work on global coronal magnetic field estimation using Bayesian inference. So this work is done by me and Weber Pant and Inigo Arrigue. So as we know that the coronal magnetic field is a major driver of the space weather and it plays an important role in the formation and dynamics of the solar atmosphere. But the highly dynamic nature of the solar corona and the weak strength of the coronal magnetic field makes it difficult to estimate. But there are different ways to estimate the coronal magnetic field. First is by extrapolating the photospheric magnetic field by making use of the potential field source surface or by making use of force-free field approximation. And the second one is by making use of coronal magnetoseismology. So this method actually makes use of the magnetohydrodynamic waves and oscillations that are observed in coronal loops and the coronal structures. So from MHD, the observed parameters can be used to infer the average magnitude of the magnetic field strength of these structures. So there are different studies which evaluated the coronal magnetic field, but in one study, that is by Yang et al. 2020, so they obtained the global map of the coronal magnetic field in the solar corona. So I'm not going into much details of this, but giving an overview of this, they make use of the Doppler velocity data corresponding to 14 October 2016, taken by COM. So using this Doppler velocity data, they estimated the phase speed of the propagating galvanic waves in the field of view by making use of wave tracking technique, and then they obtain the density, electron number density in the solar corona by using the intensity ratio of 10798 angstrom and 10747 angstrom. Since we have the density information as well as the phase speed, then we can obtain the magnetic field information in the field of view. But this method makes use of the exact values while interpreting the magnetic field. As we know that the solar corona is very much dynamic and it is better to consider the distribution rather than point estimate of density. And along with the distribution, it is better to consider the probabilities of each value of density. So here comes the Bayesian inference to our rescue. But before going further, let us understand what is Bayesian inference. So Bayesian inference is a mathematical approach through which we can estimate a parameter or we can compare the models. So this makes use of the Bayes theorem. So Bayes theorem is basically this formula. So if we have the information about a particular event, so that will be included in this prior probability. So using this information, and suppose we have some another event, given that event A has already happened. So using this product of these two probabilities, we can find out the probability that this event A will happen given this probability B. So this denominator is just a normalization constant. So it actually helps us to update our probability, this posterior probability, if we get the updated probability of this event. So in our analysis, we use the magnetic field range from 1 to 8 Gauss. So this range is actually obtained from the simple inversion. And we consider that at each pixel, all the values from 1 to 8 Gauss are equally probable. And for the density, we use two different priors. First is the Gaussian prior and another one is the uniform prior. So for the Gaussian prior, since we had already information about the density at each pixel. So we consider that information as mu and the uncertainty in density as sigma. So we consider the probability on the density like this. And for the uniform prior, we consider that the all the values from mu plus 3 sigma to mu minus 3 sigma are equally probable at each pixel. So for the first case, in which we have the uniform prior in magnetic field and the Gaussian prior in density, we find that the joint probability distribution of magnetic field and the density like this. So here, the joint probability distribution is maximum, corresponding to which the probability in the density is also maximum. And for the second case, where we have the uniform prior in magnetic field as well as uniform prior in density, so we obtain this kind of joint probability distribution. So one thing is clear that the shape of this joint probability distribution is actually depending upon the different priors on density that we use. And if we integrate along this axis, means if we integrate along the density, we obtain the marginal probability of the magnetic field and the magnetic field corresponding to which the marginal probability is maximum, that we call the most probable value of magnetic field. So in this 3D map, here this third dimension is actually the magnetic field. So we obtain the marginal probability at each pixel. So here the height of this bar that corresponds to the probable values of magnetic field, and the color that corresponds to the marginal probability at that pixel. And that marginal probability is corresponding to the maximum value of this field at that pixel. And if I plot the marginal probability distribution, uh, here you can clearly see if this dot dash line that is corresponding to the magnetic field obtained using the simple inversion, and this solid line corresponds to the uncertainty in the magnetic field obtained using simple inversion. So this we can see that it is giving only the point estimates of the magnetic field. But these solid black curves, these corresponds to the magnetic field probability obtained using the Bayesian inference. Uh, and here, these three pixels are actually few out of the few exceptional cases for which the most probable values of magnetic field for these two priors and densities differing. So if I plot only the most probable values of magnetic field in the whole field of view for two different priors and density, so I obtained this type of maps. And if I subtract the magnetic field obtained using simple inference from this, I found that the magnetic field in the whole field of view is this difference is approximately zero. And if difference lies, that lies either at the edges of the field of view or near this occulter region. So, what could be the reason of this? So, the reason is the density or the uncertainty in the phase speed is large at the edges or near this occulter region. And we also obtained the variation of marginal magnetic field along with this magnetic field because we wanted to find out where the values are most probable. So we found that the lower values of magnetic field are actually most probable in the outer regions. As you can see that the 1 goes is most probable in the outer regions, and around 1.5 goes the magnetic field is concentrated along these flux tubes, and the higher values of magnetic field, these are probable near the inner region, means near this occulting disk. We also plotted the variation of magnetic field strength along these coronal loops. For that, we selected coronal loops from the intensity images. We selected these four coronal loops, and we found that as we move away from the foot points, the magnetic field strength actually decreases. And this decrease is not uniform. It actually decreases as we move away from these foot points. And we also tried to plot one case for the loop 3, which is near the occulting disk, and this length of the loop is quite small. So here you can see that this variation, like here, is not visible because this loop is very small. And we also plotted the magnetic field across these loops. So here we selected the midpoint of these loops and we selected a slit perpendicular to this. And we found that as the slit passes across coronal loop, then at that point the magnetic field strength increases, and then as it moves out of the coronal loop, the magnetic field strength decreases, and again it increases when it encounters a coronal loop. So, moving on to the conclusions, we found that the Bayesian inference that uses the whole distribution of over the density, and it also gives the a whole magnetic field distribution along with its probabilities. And we found that the marginal probability distribution curve is not always perfectly Gaussian, but its shape depends upon the prior density distribution. And also, we found that the magnetic field obtained using the simple inversion is, at some points, it is different from the most probable magnetic field using the Bayesian inference. And this happens only in the cases where the errors in density is significant. And the higher values of magnetic field are most probable near the base of these coronal loops. Thank you.
We've got lots of time for questions. Sarah put something in the chat first, and then Alan.
Yeah, just wondering about the magnetic field you measured in the loops. Did you look at like the radial variation? Was it falling off? Like what kind of slope was the magnetic field falling off in the loops?
Okay, so actually I tried to obtain the radial variation of coronal magnetic field, but I didn't show it here due to time constraint. So this kind of variation I obtained. So here you can see that this power law index is approximately same for all the three distributions. Means for two Bayesian and as well as the simple inversion.
So there's some variation between them, it looks like, although is it within
Sorry?
error bars? I'm just looking at how they vary within error bars. It looks like they're pretty similar.
Yes.
Thank you.
Hi, nice statistics. I was wondering what is the physical relationship between plasma density and magnetic fields, and why should the magnetic field value be tied to a plasma density value?
Okay, so as you can see here, the plasma density is the magnetic field value is actually depending upon this plasma density. If we consider that these waves are galvanic in nature, so if the plasma density varies, then the magnetic field density will also vary. Am I able to answer your question?
Yes.
You don't seem convinced. Okay, you don't want to follow up. Maybe.
Can I follow up with a
Yes,
question
please,
then?
please.
With that explanation, with I assume this is comp data.
Yes,
So you're
yes.
so you're using Doppler and transverse velocity to really get that Alfvén speed. And the density diagnostic is a completely different thing. So it's like completely different data sets, completely different time scales. So obviously there is a connection from a analytical point of view, which is why you're showing the equation. But what's your
Yes.
take on the connection? Well, you just gave your take on the analytical connection, but what about the data-driven connection? Why should the density diagnostic seen in comp data or UComp data be related directly to the magnetic field information that you deduce from comp data or UComp data?
Actually, this density information, density diagnostic is done on the density information that we obtain and at just half hour difference. Means this 10798 images were not available at the time when when this phase speed data was available. Means 10747. So the time difference was not that much. So like. So I don't think that this will make a huge difference in the density information because we are considering the quiet sun only.
Yeah, so that
Yeah.
answers my question. The assumption is within that 30 minutes of completely different data sets, you're still assuming that even though the Alfvén waves are moving within that hour or an hour and a half, then around 30 minutes later or something, 1079 starts getting taken, and then you use the density diagnostic, and so that gap in time is still you're saying it's negligible. So that answers my question.
Yeah, it's not that much.
We have two hands raised in the chat.
True test. Oh,
Okay, let's start with Sarah.
no, let's start with.
Okay, Richard, please go ahead. Joan,
Morning, everyone. I just had a question about your likelihood function. So I kind of missed what it was. I saw the slide, but I didn't take any notice of it. So your likelihood function, it's focusing on The likelihood of the velocity, the phase speed measurement, is it?
Oh, the where the likelihood function is at the top, and she had the annual annotations. Is that what you're saying? You want her to pull up that slide?
Yeah, yeah.
Yeah.
Sorry,
So-
which one?
This one is fine. What's the likelihood function you use?
The top left, I think, is the likelihood function.
I know that's just a general probability expression. Though. I mean the actual density distribution.
Oh, that's what he wants. Okay.
Yeah, that's what I was gonna ask you.
So what do you use for the likelihood function? What density distribution?
So actually, at density distribution, like I had the information of the density at each pixel. So, like I selected the density in this range, and then for the likelihood, I use this model, that the Alvanic phase speed model, and then I obtain this likelihood. So I
Okay, let me
consider
rephrase
that.
the question. Sorry. What's the probability density function that you use for the likelihood?
So
Like, is it
probability
based on
density.
Oh, go ahead. Sorry, go ahead.
Sorry. This probability density distribution here, like I consider two different density distribution. First is this quotient prior, and each pixel I'm considering the densities are different.
No, that's not quite the answer. So your likelihood function is a probability density function. All right. You
Yes.
required specified some PDF for that. I'm wondering what that PDF is.
Oh,
Yeah,
I'm
I think it
using
is
the
normally
quotient wise.
distributed. Upasana, you have taken a normal
Yeah.
distribution, right? From
Yeah,
the
yeah, quotient wise.
Yeah, can you answer that? Yeah.
And what did
Yeah,
you?
so-
How did you deal with the uncertainties on phase speed in that? What did you use?
So the uncertainty that I obtained in the phase speed, that was due to the fitting error.
All right. Okay. Okay. Yeah. All right. Thank you.
Well, it's appropriate. Matthias raised his hand just a split second after me. So I was just going to suggest that a stronger magnetic field has the capacity to contain more plasma. And I was going to ask Matthias what he saw in his model. And then you raised your hand a split second later.
So I just want to make the suggestion that for the questions raised here, it might be very useful if you kind of use the numerical simulation as a test bed for testing these sort of data interpretation methods. I mean, you have numerical simulations of active regions that you have IP waves in there, so you could make a synthetic computation of these comp lines and apply exactly this data analysis to the simulation and see how much you get compared to what actually is in there. You can check which distribution of your density probability distribution is most meaningful.
And Shen Yu has done some forward modeling with Baofeng waves, right?
Yeah, Shen Yu
Yes.
introduced these kind of ironic waves in the awesome model, and we can do a forward modeling to compare with UConn observation results. And it's basically the non-excited emissivity weighted magnetic field.
You guys hear that online?
Yeah. Yeah. I could hear that. Yeah.
Any other questions?
Richard?
It was
Oh,
just to
Richard, go ahead.
follow on from Matthias's point. So, from an observational perspective, in active regions, you really only see standing modes, and you see the propagating waves in the quiet sun. I don't know why this is the case, but quiet sun data seems to be full of propagating waves. Active regions only seem to show standing modes. So then the technique that we use here is not going to work for active regions because we rely on wave propagation. So if the simulations are reproducing the same alphenic waves that you see in active regions, then the simulations might only contain standing modes. So that's something to watch out for in that comparison. Just a comment.
Richard, I don't know if this is true for comp or UComp observations. I know in AIA observations, we usually see standing mode in active regions, but is that also the truth for UComp observations because they are at a higher height? maybe because in lower height you have a very fast RN speed, so the standing mode can be really quick to form. But is that also true for higher region?
Yeah, so the loop lengths from AI data are comparable to the comp loop lengths. So it doesn't seem to be loop length dependent.
Wait, are you saying if it's comparable to comp, are you saying that we're not necessarily seeing, you're questioning the alphanic waves?
Only in active regions. I'm not saying they're not alphanic waves, I'm just saying when you look at AA data, which seems to be the best for sort of probing active regions, at least, then people have only found standing modes. They've not found any evidence of wave propagation. However, when you look at the comp data, which is vastly made up of the quiet sun, then you see wave propagation everywhere. So there's.
But what if we're above an active region? What if we're looking specifically right above an active region?
Can't say in that specific case. Yeah, I don't know. It would be interesting. I don't think anyone's done a one-to-one comparison between active regions in comp and SDO data just to see what the signals do look like. It's a bit of a mystery. I can't explain why this appears to be the case, but it's just something that seems to be there in the literature, at least. These two things.
All right, thanks.
Well, let's thank Upasana again.